I'm Ankur Moitra. I'll be telling you about some work I'm pretty excited about. This joint work with some really excellent collaborators, Ainesh Bakshi, Alan Liu, and Morris Yao. So today what I'm going to do is I'm going to tell you about one of the most basic and fundamental problems in control theory, something that's been studied for over 50 years. But shockingly, there are wide gaps in our understanding. And I'll tell you about some exciting new algorithms that connect to a lot of traditional theoretical computer science tools. Okay, so first I want to introduce what a linear dynamical system is, and then I'll tell you why they're important and they show up in all kinds of applications. So a linear dynamical system is defined by these two equations. So the important thing is that there's a hidden state that's evolving over time. You should think of that as an n-dimensional vector. And then we also get inputs and outputs. So the input is also a vector, and the output is also a vector. And the catch is that we don't see the hidden state. We don't see what's happening behind the scenes. Now, each of the matrices in these two defining equations have a special name and has a special role. The most important of which is the A matrix, which is called the transition matrix. This describes how the system would evolve on its own in the absence of applying control or disturbances. So a lot of the spectral properties of the transition matrix govern things like its long-range dynamics. I'll be particularly interested in what are the minimal conditions under which it's possible to learn a linear dynamical system. Now, the other matrices that have an important role, this matrix right here, B, is called the control matrix. That describes the relationship between what kinds of control we exert on the system, and how it affects the hidden state. And then we have these sensing and feed-through matrices that describe the relationship between our observations and what's actually happening in the system. Last but not least, all of this is not a deterministic process, so there's noise, both in how the system evolves, that's called process noise, and we have noise in our observations, that's the observation noise. Just to keep things simple, you can think about all of these noises as being Gaussian random variables, but everything I say will extend well beyond that case, but let's keep it simple. So these are the two defining equations for a linear dynamical system, and we'll have to use them and exploit them to get efficient algorithms. But especially if you've never seen a linear dynamical system before, I want to give you some intuition for why they show up all over the place. Yeah? UT is the input, that's right. So UT is the input, YT is the output. The important thing for a linear dynamical system is that this is what we see. We see the input-output behavior, and we'd like to learn something about what are the underlying dynamics, how they're governed. Yes?
Are there any relationship between the matrices like A and C?
I'm not going to assume anything about it, but just to get a warm-up, let's think about what these look like in special cases to see that this is a very natural setting. So the most famous example of linear dynamical systems in action was that they were used in the literal moon landing. So in fact, here what happens is that we're tracking the trajectory of the spacecraft from the Earth to the moon. And the trouble is that we want to know what its position is at all times, but our measurements have a huge amount of noise. You can see they have a giant amount of noise compared to where the actual true trajectory is. Now, instead of just instantaneously eating that noise, we can use information about the underlying physics to get better estimates. Because the trajectory, of course, in reality is smooth, so that can help us denoise. In fact, even better, it satisfies Newton's laws. So the thing that you do is you encode this as a linear dynamical system. So what's the state of your spacecraft? It encodes all the relevant information. What's the position? What's the velocity? What's the acceleration? And then your A matrix, the transition matrix that defines how your system would evolve on its own, well, this is really an abstraction of Newton's laws of motion. It's an upper triangular matrix with ones along the diagonal because of the way that the velocity changes the position and the way that the acceleration changes the velocity. That'll be very critical that this is an upper triangular matrix. I'll come back to that later. But this is really a landmark application. Every control theorist will tell you that their field was used in the literal moon landing, and it won the National Medal of Science in 2008. And even better, the Kalman filter is something that gives you a good estimate of the trajectory. In fact, it's statistically optimal and computationally efficient, so it has all the decorations we could ever want. There are also, applications in, natural sciences in areas like biology and epidemiology, or maybe there are ecosystems or other kinds of dynamics we want to understand how they're evolving. So in fact, there's one particular, epidemiological process that we've all been interested in for the last, 4 years, which is the spread of diseases. So the world's simplest model for how diseases spread is what's called the SEIR model. So you take your population, and it's stratified into these 4 different categories, whether each person is susceptible, they've been exposed, they're already infected, or they're recovered. And then your state vector just describes how many people from your population are in each of these different categories. And your transition matrix A describes the dynamics of a state machine. What's the probability that you move from one state to another? In fact, even though the SEIR model is very simple, there are a lot of extensions of it which are quite powerful, like the one that I'm depicting right here is from a very recent study, where what they do is they fit an age-stratified SEIR model, where depending on what age group you're in, you have a different underlying state machine for your probabilities of making these transitions. And they find very good fits to things like, different waves in Stockholm and so on. And then let me tell you one other cool application just to drive the point home that LDSs are everywhere in the world around us. There's the super cool application that I learned about from Ben Recht, where you can think about medical applications where I have some drug and I want to understand its efficacy. So I want to know how effective this drug is, and the gold standard for what evidence is in the medical field is you do randomized control trials. So you take a large cohort of patients, and then you randomly split them up into 2 groups. One group you give the actual drug to, the other group you give the placebo. And you measure the outcomes in these different groups, and you use this as a way to estimate things like p-values for how likely you think the drug is effective. Now that's great when you can do a randomized control trial, but the trouble is that when I'm using certain kinds of medications, they react in a very person-specific way. So when you want to understand whether the drug is actually effective for you, as opposed to a random other person from the population, it's hard to actually interpret the results of these studies. In some cases, it's literally hard to find, large cohorts of patients because there just aren't that many people, with these particular conditions. So it turns out that there is still something you can do, but it involves exploiting the dynamics. So for example, for pain medication, people do what's called an N of 1 trial, where there's just one single patient in your study. It's you. I want to figure out how the pain medication works for you. And what I do is week to week, I randomly decide to give you the pain medication or a placebo, and then I measure the time series response that you report. And I try and learn a linear dynamical system that fits this data as a way to understand the efficacy of different drugs. So there are all kinds of other applications like speech processing, econometrics, finance even. But hopefully this gives you, a bit of an introduction to why LDSs are so important. These aren't traditionally things we talk about in computer science, but they're very cool. And really just to take a step back, we have these 2 defining equations that we hopefully understand by now. And really when you have an LDS, there are 2 things you can ask. And this is kind of what makes them powerful. See, in the setting where the parameters are known, if I told you the matrices A, B, C, and D, then you can study an inference problem. That's like the space shuttle example. I know what A is, I know what B is because I designed the spacecraft. And what I'm observing is the sequence of inputs and outputs. And what I want to do is I want to infer what's the hidden state. So there are wonderful things like Kalman filtering that that tell you that that you really can estimate the state very well, and that there are computationally efficient algorithms for doing so, and they have wonderful statistical guarantees. But the question I'll be interested in today is really the question that comes before that, right? In some settings, you know what these matrices are because they come from first principles, like physics or knowledge of the underlying system. But there are other cases, especially in natural phenomena like biology or medicine, where the real task I want to do is I want to learn the parameters of my LDS, either so that I learn something important about the long-range dynamics of my system, or so that I can do these other tasks once I have the parameters, like doing inference. So that'll be our goal, right? And the main problem is actually the obvious problem, but I'll explain it in phases because it helps to start with the intuitive description of what's the learning problem before I make it precise. So the main problem is I'm going to ask the hardest possible version of the learning problem. In fact, I want to learn an LDS from one single long trajectory. So all I get is this very long sequence of inputs, these u1 through ut vectors, and the outputs, y1 through yt. And I want to learn estimates of the underlying parameters of my LDS. In fact, I'm going to make my life even harder. I'm not even going to assume that I can control these inputs. It turns out control is kind of a misnomer. I'm just going to assume that they're passive disturbances that are applied to the system. As long as these u's are random enough vectors, we'll see that we're good. So these aren't even things within my purview to set. Now, there's this main challenge, which, if you work in learning theory, you know very well. And if you don't, let me explain it. This is my informal description of the problem. I want to estimate A, B, C, and D. Now, how should I measure closeness? I find an estimate A hat. Should I use the Frobenius norm between A and A hat? Not necessarily. Because sometimes what happens is that there are invariances of the parameters that don't change the behavior of the system. So it's not even obvious what's the right distance measure to control how close I measure the distance between my estimates and the truth. So let me make this more formal. So let me tell you what the semantics are of where this distance function comes from. Again, we're going to aim for the strongest possible learning goal, which is what I'm going to want to do is I'll talk about two sets of parameters for LDSs as being functionally equivalent if there's no way to get them to create different behavior. So even if you have an adaptive way to choose the inputs based on the entire sequence of what you've seen before, the inputs and outputs, the two different LDSs given by two different sets of parameters, they generate the same distribution on outputs up to a transformation of the noise. So this is my notion of what it means for two LDSs to be equivalent. And the thing which I'm just going to assert, but I'll give you a little bit of intuition for, is that in the case where you have Gaussian noise, this notion of equivalence has a very nice interpretation, which is two LDSs, one given by A, B, C, and D, the other given by A hat, B hat, C hat, and D hat, are equivalent if and only if there's a change of variables so that you map one into the other. So the way to think about this is what's going on here. I've got this invertible transformation U, and A hat are conjugate to each other. See, I never see the hidden state. So in principle, I can rename what's happening in the hidden state as long as I never see a change in the output behavior, right, or the input behavior. So when I multiply C times A, that describes the actual observations I see, and exactly this U and U inverse cancel out. So this is really what it means for two LDSs to be equivalent, is that there's a change of variables so that they have these natural conjugation properties.
Sorry, what does it mean up to transformation of the noise? You're allowed to change the variance?
That's right, that's right. So this is a bit of a subtle point, so I don't want to get too much into it. But if I have Gaussian noise, then the actual covariance of the Gaussian will transform with U. So what I'm doing is I'm not saying I want to learn the covariance of the noise. Up to the equivalence of I can set a covariance for the noise. The two LDSs are the same. If I assumed the noise was in some canonical form, then it's different. Yeah?
Are there equivalents of this proposition for other kinds of noise?
No, that's false, actually. Because if you had some kind of discrete noise, then they wouldn't really have any kind of transformations this way. But it'll turn out that if you don't have nice noise, there can be computational or statistical gaps, but that's a bit of a technicality, and let's table it, but great questions. All right, so now we can be formal for what our learning guarantee is, because it's the obvious thing. See, this leads to a distance measure. What I want is I want to learn the parameters up to the distance function I just argued, where it comes from syntactically, up to some epsilon. In fact, what I want to do is I want guarantees, both statistically and algorithmically, that are polynomial in all of the relevant things. They should be polynomial in the dimensions of my system. They should be polynomial in 1 over epsilon, where epsilon is this target accuracy as measured by this distance measure. And despite the fact that this problem has been studied since the 1960s, shockingly, the sample complexity, even that was open, which is very surprising. But I'll tell you more why that was true. Yeah. Yeah.
You mentioned this. Is the U unique?
So the U is unique. The U is unique. Up to some, like I think maybe, okay. So there's some cases where it might not be unique, where like maybe you have repeated spectrum and then you have certain kinds of transformations that preserve the eigendecomposition. But you should think like in a generic case it will be unique. And when it's not, you can define the equivalence class, up to it. Okay.
Am I correct that if you go from T observations to KT observations, the same as tensoring all these matrices with a big identity?
We'll get to that. So it has some similar structure. It's not quite that, but you're definitely on the right track. So we'll get to that in a few slides. Okay, so it's no exaggeration to say that there have been thousands of papers written on learning linear dynamical systems. Because it started off in control theory, where the guarantees were mostly asymptotic in nature, where they took the sample size, the trajectory length to infinity. So they don't actually know anything about finite bounds. If I just want up to some epsilon accuracy, can you get a polynomial relationship? Now recently, for reasons I'll explain more later, there's been this revival of interest because of connections to recurrent neural nets. So there was another explosion of papers on the topic of learning linear dynamical systems, but with the emphasis on proving non-asymptotic bounds. Now, I can't summarize all those papers for you, but I can tell you that there's one key assumption that happens in almost every paper, maybe all but one, and that assumption is very bad. It's terrible. And it's going to sound like it's just a slight switch from an assumption that's more reasonable, but what I'll do is I'll explain to you what that difference in the assumption is and why you should not like it too. So I told you that the transition matrix is the key, right? So what we can look at is the spectral radius of the transition matrix. So the largest absolute value of any of its eigenvalues. I want to emphasize that in general, the transition matrices we care about will not be symmetric. So this is really the max eigenvalue, not the singular values. When the spectral radius is strictly less than 1, we say that the system is strictly stable. When it's less than or equal to 1, we say that it's marginally stable. And what I want to convince you of is that in this table, this is bad and this is good. So let's do that. I claim, and we already can see this, that the spectral radius being, it being strictly stable fails in even simple and some of the most important cases. Why is that? What's the most famous application of LDSs is to tracking the space shuttle motion. What was that transition matrix we got? Remember I told you it was upper triangular with 1s along the diagonal. So it definitely has eigenvalues of value 1. And in general, when you discretize many kinds of ODEs, this is what happens. Because you discretize it at a very small time increment, and then it should converge to the identity because you're not really moving. So almost all discretizations of processes that we care about, continuous things that we want to approximate, fail for strict stability. I told you that for an LDS, they can have these long-range behavior, right? And see, the point is that when we have strict stability, they literally have no long-range correlations. So what that means is if I tell you the hidden state at the start, and then I ask you what that tells me about the hidden state at some much later time, well, when I take powers of A, they're all going to 0 very quickly. So that knowledge of the initial state tells me vanishingly little. So there are no long-range correlations. And remember, my goal was to learn an LDS from one long trajectory. See, when you have strict stability, in effect, you're cheating. Because when there are no long-range correlations, it means you can just wait a long time until it mixes, and then you get fresh samples, right? Whereas marginal stability is really just the assumption that the system shouldn't explode. If I had the spectral radius larger than 1, it wouldn't make sense for the noise to be some fixed thing, because my system is going off to infinity. So actually the problem becomes trivially easy in the case where it's larger than 1, but the action is in the marginally stable case. So these thousands of papers that have like all kinds of assumptions, they have always this one assumption in there, which is that their bounds, they look like 1 over 1 minus rho of A. So they're exploding as rho of A goes to 1. And this is a very intuitive thing that shows up in their bound. This is a mixing condition. This is how long you have to wait until the thing mixes, and that's the way the analysis works. And as a teaser for later, I will show you a trivial proof that there's an algorithm for learning under strict stability. It turns out that it's a completely trivial algorithm, but it was for some reason missed. So really what I care about is this conceptual question, which is under marginal stability, we can and do have long-range correlations. That's what's the most interesting in learning from dynamics. I want to know whether long-range correlations actually obstruct efficient learning or not, and that's the goal. Okay, so I told you what assumptions I don't like. Let me tell you what assumptions I do like, because you do need some assumptions to do it, and here I have to give you control theory 101. But we'll do, a quick version, which is, I think, intuitive. In fact, it turns out that there are natural conditions, which make sense once you wrap your head around what they mean, that go back to Kalman in the 1960s. So first thing you can do is you can create this matrix. This matrix is going to play a key role in everything that comes next. This is called the observability matrix. So remember, the C matrix describes the relationship between between the hidden state and our observations. The A matrix is the transitions. So I form a block matrix which looks like C, CA, CA squared, and so on. That's called the observability matrix of order S. And what I claim, and I'll prove this informally, is that if this matrix does not have full column rank for all orders S, then you are dead. The problem is information theoretically impossible because there's some portion of the state space that you cannot see, right? So just to belabor the point, for those of you who aren't that quick at seeing this, let's just belabor this thing. Imagine that I have some state xt, and then I perturb the state in some direction z that lives in the null space of this matrix. What does that mean? So c times x is the same thing as c times xt plus z. That literally means that there's no effect on my next observation yt. What does it mean that c times a times xt is equal to c times a times xt plus z? It means that there's no effect on yt plus 1 because this describes how the system evolves over one step and then how I observe it. So what this tells me is that I can't see this change in the state even over s time steps. So if you have for all s that it's not full column rank, you are dead. And that's a purely asymptotic statement that the problem is impossible. There's one dual condition, which is the same thing, right? That's the other matrix that's going to play a key role, and that's called the controllability matrix. So remember that B is my matrix that describes the relationship between my inputs and how it affects the state. So if this block matrix that looks like B times AB times A squared B and so on does not have full row rank, what it means conceptually is that there's some direction in the state space that my input cannot push me in or out of. And it's the same proof here. It's because there's something in the left kernel. So the necessity of these assumptions, I claim, goes back to the 1960s in this landmark paper of Kalman. And what I claim is that we don't need all of these crazy conditions like strict stability or the laundry list of other conditions. These are the only conditions we need. So what I'll show you is I'll show you a new algorithm for learning linear dynamical systems. In fact, I'll give you the key parts of the proof will all be in whatever time is left. And all we're going to have to do, we can allow marginal stability. We're passively getting inputs. We don't even have to choose them ourselves. And we're just going to need quantitative bounds of these observability and controllability conditions, because you need not just that they're full column and row rank respectively, you need lower bounds on their smallest singular value, namely upper bounds on their condition number. And cool, the other cool part is that you can show that these conditions are not arbitrary, they are essential. So you can show that under a slight strengthening of it, that if they're ill-conditioned for all orders S, then it's not your fault. The problem is information theoretically impossible. So what I'm going to do is I'm going to do some philosophy for 2 slides, bear with me, and then we'll do a proof. So I told you that all but one paper made this nasty strict stability assumption and even crazier assumptions, like having the output be one-dimensional, having some conditions on the roots of whatever. I can't even state all the conditions. There was one paper that worked under marginal stability. Unfortunately, they give an unspecified dependence on the system parameters. So, you're in effect treating all of the things like the dimension of your system as constant, which is bad. And in fact, you can show that their bounds are actually exponential, even in cases where you can get polynomial bounds. But the other thing that I want to mention, just from a philosophical standpoint, is, why was there this interest in control theory, and then it dipped off, and then it had this huge, popularity increase? Was because of recurrent neural nets. So recurrent neural nets are like a non-linear version of what I was telling you about. And when they started becoming very practically relevant, people wanted to prove things about how gradient descent works. Now, the trouble is you can't really prove anything about things with non-linearities. So what they did was they studied linear dynamical systems as a metaphor for how gradient descent works in the recurrent neural net case. But there's a big problem with that, which is when you try and study it as a metaphor without understanding the algorithmic limits to begin with, you might totally miss questions like, what are the minimal assumptions? You pick up these conditions like strict stability, for which reasons I'll explain, they trivialize the problem. So these, intuitions about gradient descent were, kind of missing a little bit of, a very important nuance that you wouldn't see. All right, so I have one more slide on philosophy. I don't usually think about control theory, but I've been thinking about it these days. But, I spend a lot more of my time thinking about, unsupervised learning. And there's one blueprint in unsupervised learning that's been extremely powerful. It's a blueprint that goes back to the founding of statistics back in 1894. It's called the method of moments. And it works as follows. You have some parameters of some distribution you want to learn. And what you do is you take a bunch of samples from your distribution in order to estimate the moments. When you have these estimates of the moments, you set up a system of equations and the unknown parameters you'd like to solve for, and then you solve them. So Pearson invented this approach. He only gave heuristic analyses of what's going on. But over the past 15 years, there's been huge progress in analyzing the method of moments and giving rigorous guarantees, for Pearson's original question, like learning mixtures of Gaussians, and all kinds of other unsupervised models therein. Hidden Markov models, topic models, robust estimation. So this is our standard playbook in unsupervised learning. We use the method of moments to get efficient algorithms and sample complexity. But I'm lazy. What I want to do is I want to understand whether there's a version of this recipe that works for non-stationary data. See, in unsupervised learning, there's one fixed distribution, and you get as many samples from it as you want. But the trouble in a linear dynamical system when you have one long trajectory is that the system is never settling down. It keeps changing perpetually and moving around. So what happens when the data is never in place? Is there still a way to get the method of moments to work? Maybe we can forget about gradient descent on these non-convex parameterizations. And what I'm going to do is I'm going to follow this very simple blueprint. I'm going to estimate something called the Markov parameters, and then I'm going to use the Ho-Kalman algorithm. That's my entire algorithm. So the Markov parameters are described by this block matrix. Last block matrix I have to tell you, well, no, second to last. And this right here, the way to interpret it is it's the input-output behavior. So C times B describes the relationship between my inputs and the outputs. C times AB describes the relationship between my inputs and the time-lagged output by one step. And all I'm going to do is I'm going to take a bunch of samples to estimate these Markov parameters that I'll call the moments. And then I want to go from these estimates for the Markov parameters to the estimates of my LDS. In fact, I'm really lazy. In fact, step 2 has already been done in the 60s. for the life of me, I couldn't understand the proof in that original paper. So I'm going to give you a different proof, which connects a lot more to like modern methods in learning theory, because that's really what's happening in disguise. So let me tell you about this old proof that I can't read, but I presume this is what's in the paper, probably. So this is the Ho-Kalman algorithm. So remember where we are. Someone gives me the Markov parameters. They tell me D, you can forget about D. They tell me CB, CAB, CA squared B, and so on. And I want to go up to, I want to deduce from that estimates, A hat, B hat, C hat, and D hat. Now the same things that I belabored before, you have to choose the right parameter distance, are going to show up here. I can't just hope that my Ho-Kalman algorithm is going to find the right A. It can only find the A up to that similarity transform that we argued about, has this right semantic meaning. So somewhere in this algorithm, that's going to have to pop out too, the distance measure. Now I'm going to do one thing which may look very strange if you haven't seen it before. I'm going to take all of these estimates that someone handed me for the Markov parameters, and I'm going to organize them into this Bloch-Henkel matrix. You shouldn't see why I'm doing that, but we'll get to that. So, they're organized into like CB, CAB, CAB, and so on along these anti-diagonals. And I'm also going to call all but the last block column H1, and I'll call all but the first column H2. So just bear with me about the notation, but let me give you some intuition. See, the key is I know this matrix because someone gave me the Markov parameters, and I claim it has a hidden factorization that I wish I had. So that's the relationship to trying to solve the parameters. Remember, I had these two key matrices, the observability and controllability matrices. This one was C, and then CA and CA squared, and so on. This one was B, and then AB and A squared B. So when I take the product of these matrices, I get the Henkel matrix, right? That's literally just true. And this is the hidden factorization we're looking for. So all I have to do is find any other factorization and argue why it should be equivalent in the parameter distance I care about. So can we compute another factorization and show it's equivalent? So let's take that H1 matrix, which just removes all but the last block column. Removes the last block column. Let's just apply the SVD to it. I'll write it as U sigma V transpose. That doesn't look like the product of two things. So I'm going to take V and split it into two pieces, V to the 1/2 and V to the 1/2. And very suggestively, I'm going to call this first part O hat and the second part Q hat, because I hope that this is close to the true O, and I hope that this is close to the true Q. But remember, I can again play this game where the product, the actual factorization, the same way H was an actual product of O times Q, same thing for H1. It's just that I'm going out to a different order because I removed the last block column. So it's OS plus 1 and QS. So now let's do a very elementary statement in linear algebra, right? What I claim is that if O and Q have full column and row rank respectively, then it must be the case that O hat and Q hat do too, and that there is a change of variables, there's a linear transformation, so that after that they're equivalent. If that were not the case, then they wouldn't have the right, row and column space. So this is a purely elementary statement in linear algebra. There's nothing that's going on in this, but this is the key. This is our similarity transform that we're going to argue. We're going to learn all of the parameters A hat, B hat, C hat, and D hat up to this relationship, right? So now I know how my O hat and Q hat that I found when someone gave me the Markov parameters relates to O and Q. And then we only have one more step left. Let's find A. So what do? I just put it together. I define this thing called H2, so I should probably use it. H2 is the product of O times A times Q. So there's always at least one power of A when I remove the first column, so I can definitely put an A in there. And now I can use what I know from step 2, that O is related to O hat by the similarity transform. Q is related to Q hat by the same similarity transform. And O hat and Q hat have full column and row rank respectively, so that means they have left and right pseudo-inverses. And I can compute those. And I can multiply by them by H2. And what will that give me? That'll give me A hat, which is equivalent to A up to the same similarity transform. So this is, I think, in that paper from 1960. But this is connected more to modern learning theory tools where we use a lot of generalized eigendecompositions in order to get algorithms for the method of moments.
And so your condition number comes there in this.
It does. Well, 1 second. You're absolutely right. Let's do it. See, the thing I really care about is that whatever I do in this first step, which is where the new action will be, that's only going to get the Markov parameters up to some sampling noise. So I don't just care about the fact that if I had the exact right things, I would get the exact right things. I care about the stability of it too. Because I want the guarantee that when I drive this down at an inverse poly rate with the samples, I get estimates converging to the true thing going down at an inverse poly rate too. Believe it or not, this was only proven like 4 years ago. I think it's a very nice paper, but the intuition is very straightforward, right? Because what was I doing there? I was computing the SVD, and when is the SVD well posed? It's when those things are well conditioned. So as long as I have the condition number of observability and controllability, it's not just that we reason from first principles that they must be there for the problem to statistically be true, but it shows up intrinsically in this algorithm. Writing down the stability bound that you prove would take me a full page, so let's just say it's stable. So I haven't told you anything new yet, right? But the main challenge is just where do you get these Markov parameters? And this is where the action will be. So what I'm going to do is I'm going to convince you that it's trivial, but I'll have lied. So there's a really important catch. So I told you the Markov parameters describe the input-output behavior. That's literally true. Shockingly, I haven't seen this observation written, but it's a totally trivial observation. That imagine that I just assume that the inputs have identity covariance. There's an equivalent version of this when they don't, right? But this doesn't even use Gaussianity or anything. If I look at the covariance between my input at some time t and the output at some time-lagged t plus j, I claim that as I vary j, I'm going to sweep out all of the Markov parameters. Once you state this, there's only one way to prove it. You just expand the recurrence, right? So let's do it for j equals 1. I have my first defining equation that defines yt plus 1 in terms of xt plus 1, ut plus 1, and zt plus 1. I don't see any ut's there, so I'm going to expand xt plus 1, and now I have my ut. And the covariance between ut and everything else but that term is 0, because they're independent. And so when I took the covariance with respect to ut, that's the term I pick out. It's cb. And as I increase the gap between them, I sweep out all the parameters. I get higher powers of a. And this is the intuition, right? So it sounds like we're done, right? We have an unbiased estimator for the Markov parameters. And I already told you why when we have the Markov parameters, we're done. Well, it sounds like we're done, right? Because what do you do when you have an unbiased estimator? You obviously add them up and average. That's what we always do, right? So each one of these is an unbiased estimator for this, so I add them up and I average. I claim this does not work. Can anyone make me very happy and tell me why it does not work?
Because the noises are no longer independent.
Yeah, who says that the variance is going down for this? That's the whole point of the problem. That's the entire point of the problem, right? The time series is non-stationary. So who's to say that you're adding these things up and the variance is decreasing? That's just false. But what's the other thing I owed you? When it's strictly stable, problem is trivial. You don't have to do gradient descent on a non-convex objective function. You just wait long enough until you get independent samples, and that's it. So these thousands of papers that were analyzing gradient descent to try and understand RNNs didn't realize that the problem is trivial in the case they studied it. That's weird, but it's true. But let's try to be better. So in fact, here we're going to use an idea from control theory, which is that didn't work before because my variance wasn't decreasing. I'm going to try and control my estimator. So I'm going to engineer a new time series. So I'm going to choose some coefficient Cj so that I create a new time series on the y hat t's, which hopefully fix my problems. They should maintain the invariant, that they're unbiased estimators of my Markov parameters, because that's why I'm doing what I want to do to begin with. And I want them to have the property that they make the variance bounded independent of t. See, the intuition is that it's true, the time series is growing and changing. But if I knew the time series, it would imply that there are good CJs. So I can hope to write a convex program to search for these CJs that stabilize my estimator. So this requires a few attempts, but let me give you the key idea that once you see this, you'll believe that it can be made to work, even though it doesn't work. Let's do something smart. Let's choose the CJs to be the coefficients and the characteristic polynomial of my transition matrix. The key is the Cayley-Hamilton theorem, because every matrix satisfies its own characteristic polynomial. What that really means for our purposes is that a high power of A, if it's an n by n matrix, a to the n, can be expressed as a linear combination of lower order powers, and those coefficients are given by the things in the characteristic polynomial. So let's use Cayley-Hamilton to see why we can stabilize our estimator. What I claim is when you engineer the time series this way, this new y hat, you create an epic amount of cancellation, or you cancel all but the transient terms. Now the proof of this is just write down a giant equation, but I tried it and I couldn't fit it on the slide. I tried it again, I still couldn't fit it on the slide. But let's just make the equation as simple as possible to see why it should be true. I'm going to ignore all noise terms. I'm going to set my D matrix to 0. Let's just pretend our time series were given by these two defining equations, these two equations right here. So now I take my new engineered time series, y hat t plus 1, and I have these coefficients that come from my characteristic polynomial. Let me just try and organize things in a way that I see the cancellation. I have, I relate y's to x's, and I get these different xt plus 1, xt, and so on. And then let me put them on a grid, because I'm really going to want to care about what happens to the ut terms. And let me do the same thing. Let me take this term and unroll it. I get a ut and an xt. Let me take these two terms and unroll them. I get ut minus 1s and xt minus 1s. Let me unroll these. I get some more stuff. So if you just notice the pattern of what's going on, I have a very high power of A, and then I have lower order powers of A with the coefficients that cancel them out, right, from Cayley-Hamilton. So even though there's no hope of canceling out the transient terms, eventually I get cancellation. And so when you work that out, what that means is you have this giant zeroing out, and now I have a small number of terms that can't be canceled out. The important thing is that how many of them are there? There's a fixed polynomial number that's independent of the length of the time series. So this solved my first main problem, right? I stabilized my estimator so that I got a variance bound that was independent of t. Just to finish up with the sketch of how this works, this messes up the expectation. If I write down the equation I had on the previous slide, I canceled out a huge amount of things. But the trouble is that if I look at the covariance between y hat t and ut minus I have one of the Markov parameters that I wanted, but I also have this. And that's not what I want, right? But there's a very simple fix for this, which is instead of literally canceling using the successive previous things, why don't I just wait a little bit? So if I only want some fixed number of the Markov parameters, I'm going to wait a little bit before I start doing the cancellation, right? And the claim is that if you wait long enough, then there is no ut minus 1 in this term because it just hasn't happened yet in the time series. So this way I can get all of the Markov parameters I want, but just instead of canceling with the characteristic polynomial, cancel with something else. So the expectation is unchanged, and we're almost done. So we have the third attempt, which sounds a little strange because I only had 2 problems, and it seems like I fixed them, but I lied again. So the trouble is that no one told you the coefficients of the characteristic polynomial should be polynomially bounded. That's false. So it turns out what you can do instead is the CJs are not scalars, they're matrices. And then you can use the fact that the observability and controllability matrices are well conditioned to show the existence of bounded CJs that still create that cancellation. That's literally what bounded condition number means. If I extend the observability matrix and I had well-conditioned full rankness, that means I can fold that in as a linear combination of what came before. So we're almost done because it sounds like if we already knew the observability and controllability matrices, we would have proven the existence of good CJs that stabilize our estimator. Trouble is, I want the O and Q to begin with. That's the entire point of this exercise, right? So the last trick is kind of the natural thing, is that what I showed for you was that the CJs exist. So let's write down a convex program to search for them. Let's pretend they're scalars even though they're not. I'm going to look for a choice of not too large scalars so that when I create this engineered time series, it remains bounded independently of little t. And what you have to argue is that not only is the true parameters we're looking for a good solution that actually stabilize the estimator, but any feasible solution to this convex program stabilize the estimator. And basically, that argument I gave you about cancellation, it leads to some potential function, which tells you how much you've canceled things out. You have to reason via anti-concentration that if you didn't create the right cancellation, there would, with high probability, be some constraint that's not satisfied. And you have to do some nets and anti-concentration and whatever. OK. So let's do some very brief philosophy. Let me check the, OK, we're OK. So this was good. The method of moments solved a very basic problem that's been open since the beginning of control theory. And one thing I'm really excited about these days is not just this particular problem, but I think maybe there's a dictionary between the tools we have in theoretical machine learning, specifically for unsupervised learning, and what happens in the dynamical case. So maybe there's a way to map all of our latest and greatest tools about the method of moments to dynamical settings. There are also some other cool questions you can ask about time series. Say, like, one basic problem in statistics is called change point detection. So you have a coin that's p-biased, and at some point, when you're flipping it, its bias changes to q. And you want to figure out where the bias has changed. You want a small confidence interval localizing the change. That's called change point detection. What about change point detection between linear dynamical systems? What if I have one virus, like COVID, the example we told you about, and then there's a new strain that spreads differently? And I'm seeing how the time series is evolving in different ways. Can I localize when there's been a switch? That's the same kind of thing. The way that you find change point detection is through a Chernoff bound for a coin. But that really is built on top of having good confidence intervals based on learning. So once you can learn a linear dynamical system, then you can ask all kinds of things here. You can ask the change point detection version for LDSs. You can ask about heterogeneity and mixture models. And I'll just say that there's even more to say about RL, where there's a lot of algorithmic things mentioned in these days. But come talk to me in a break. Happy to tell you more. So the quick summary I hope you understood was that I told you what an LDS was. I told you why you should care. I told you what there were, where were these wide algorithmic gaps in our understanding. And I showed you how there are new algorithms with minimal assumptions that work via this classic tool that we all know and love in my area of the world, and how maybe the method of moments can give us a new understanding beyond where we traditionally apply it. So I'll stop there, and thanks for your attention. Happy to take any more questions.